All right, thank you very much. I'm David Jarris, and I'm one of the organizers. It's a great pleasure to be here. And well, here means sort of here. I really am eager just to get started. This day is mostly about the calculus of variations. Its connection with waves is indirect in many situations, but certainly through eigenfunctions, it's quite direct, and eigenvalues. So we'll have several talks today which have various connections to this collaboration, and this is the first one. So without further ado, I'd like to welcome Guido De Philippis from NYU. And he's going to be talking about the title you see on your page here, Regularity of the Free Boundary for the Two-Phase Bernoulli Problem and Eigenvalues Partitions.
Okay, so thank you very much for the invitation. My first online conference after some online seminars. So yes, so this would be the topic. So actually it's pretty much linked to calculus of variation, what I'm going to tell you, and to regularity theory. So I might also apologize with the non so mathematically oriented audience, but I will also try to motivate somehow the problem. And one motivation why I ended up studying this type of problems is really related actually to the eigenvalues and to eigenvalues partition. So I will also at some point of the talk briefly mention this type of motivation, though I won't enter too much in details on that part. So before starting, just let me say, so that I don't forget, that this is a joint work with Spolaor and Velichkov. And okay, so let us start. So since it's calculus of variation, let me introduce what I'm going to study. So given three non-negative numbers, lambda 0, lambda plus, and lambda minus, I'm going to consider this functional here, which is, I'm going to call it J. So which for each function U is the energy I'm going to consider is the classical Dirichlet energy of U, so the integral of gradient U square. So actually some more complicated things can be put here, but say this is the basic thing. And then I'm going to add some penalization concerning the measure of the positive part of U, the negative part of U, and the zero part of U. Now, since everything is in a fixed domain, actually, you know that the sum of these three terms is just the measure of the domain. So basically, you can get rid of one of the three, right? Since the sum is constant, I mean, you can just absorb one of the three into the other two. But I think this way is more, I mean, the phenomenon which will appear here if I write the functional in this way. So in a sense, this is called, traditionally called a two-phase problem because you are dealing with the positive and negative part of U, but I would rather argue that this is a three-phase problem because you have all the three phases. So the positive, the negative, and the zero phase. Okay, so that's why I also prefer to write the energy in this way. And I'm going to consider a minimization problem where I'm just trying to minimize this energy J among all functions with a fixed boundary value on the boundary of the domain D. Okay? So some basic properties which are not hard to check is that minimizers actually do exist. It's a direct application of the direct methods of calculus of variation. The problem is pretty much non-convex, so you have a situation of non-uniqueness. And maybe what is more important here is to understand what the minimizer would like to do. And in a sense, the minimizer, you see, to make this term happy, you would like to be harmonic. But an harmonic function has, in principle, a very precise relation between its positive and negative parts somehow. That's the mean value theorem. So the fact that you penalize the measure of the positive or negative parts forces some balance and somehow some loss of harmonicity when you go close to the region where u is actually 0. Okay, so these are broad properties of minimizer, which are not hard to check. And maybe before giving you some motivation for this problem, let me also present a peculiar case of this problem, which is the Onephase free boundary problem, which consists simply in setting lambda 0 and lambda minus, which are the weights on the 0 and the negative phase, to be 0, and then maybe you choose the boundary data to be non-negative. Now it's easy to see that in this case, there is no reason for the minimizer to be negative. And so you are actually, so that the problem in this case, you just minimize this type of functional here. So where you just have the Dirichlet energy and the measure of the positive part, and you minimize the functional among all functions which are non-negative, okay? So this is called Onephase problem, okay? Which is a particular case of the two-phase problem, obviously, but somehow the analysis is simpler in this situation. Okay, so this type of problem, to the best of my knowledge, were introduced, at least in the mathematical community, by Alcafarelli and Alcafarelli-Friedman in the 80s. And the motivation was for the study of flows with jets and cavities. Okay, so this was, and that's why I think the name Bernoulli is attached to this type of problems. But since then, they have become somehow a prototypical problem in free boundary. So there are a family of free boundary problems which somehow can be reduced to this one, or a variation of this type of problems. And maybe I should also say why it's a free boundary problem. Well, it's a free boundary problem because the thing, and we will see this more later on, the thing your interest is exactly the transition between positive and negative, or between 0 and positive, which is the free boundary of our problem. So we don't know where the 0 set of the minimizer is, and that's actually what we would like to study. And why we would like to study this thing, so in a sense, it's really a geometric problem. I'm not really interested in the function, but much more in the free boundary. And the reason why I'm more interested in the free boundary is because, as I was saying, I ended up studying this type of problem because they're pretty much linked to some shape optimization problem and eigenvalues partition problems. So let me give here this brief presentation of what is the link, and this what should link somehow to this, also to the topic of this meeting. So let me start from a very simple example, which might be not so interesting for this meeting, but it's a starting point. So say that you are interested in this type of shape optimization problem. So you have a fixed domain D, and for each subset of this domain, call it U, you consider its Newtonian capacity. So it would be like the capacity of a conductor, which have charge 1, which has potential 1 on U and 0 on the boundary of D. And so it's well known that this capacity is given by this formula. So you minimize among all functions which are 1 on the boundary of U and 0 on the boundary of D. So the function will be 1 here and 0 here. You try to minimize the Dirichlet energy of U. So basically, the optimizer for this problem will be a function which has an harmonic transition between 1 and 0 from the boundary of U to the boundary of D. So this is the capacity of U relative to D. And now you would like somehow to understand what is the optimal shape of a conductor, which has, so you want to minimize the capacity, but okay, it's easy to see that the smallest is U, the smallest is the capacity, so the minimization of the capacity is pretty much nonsense. So you want to, let's say it's trivial, it's not nonsense. So you want to either fix the volume or, which is almost the same, penalize the volume of U. So you might want to consider a function of this type or variation of it, in which you minimize the capacity of U relative to D and some minus some constant times the measure of U, okay? So, or you fix the volume of U, and this would be the Lagrange multiplier version of the problem, if you want. So if you write down this minimization problem, what you realize is that, okay, so this is a mean problem because the capacity by itself is defined with a by a minimum problem. Now, once you have a mean problem, you can reduce it to be just a one mean problem. So you can get rid of one of the minimum. And so basically this problem is equivalent to minimize the Dirichlet energy of V minus the measure where V is equal to 1, which corresponds to my unknown set U, right? So, so this is exactly equivalent to this problem. And now it's easy to see also that there is no real reason for V to be larger than 1. So the problem, and knowing that, that the measure of my container D is just the sum of the measure where V is equal to 1 and where V is between 0 and 1. So I can rewrite this problem as the minimum of the Dirichlet energy of V plus, this time with a plus, the measure where V is between 0 and 1 minus some constant which does not depend on my function V. So in other words, if I look to the function U, which is equal to 1 minus V, well, then this function is solving a one-phase problem. So understanding which is the optimal shape and what is the behavior of the optimal shape for this minimum capacity problem is the same thing than understanding what is the shape of the free boundary for this function U, okay? So this is a way you see that a one-phase free boundary problem is related to a shape optimization problem. I mean, the construction of this conductor. So what about eigenvalues, and maybe what about also two-phase free boundary problem? Well, I might want, so let us consider this type of problem, which is a minimal partition problem. So this time what you do is that you have your domain D, then you fix a number capital N, say, and among all n tuples of subset, say 3, of D, I consider this functional here, where which is given by the sum of the first eigenvalue of the domain of the ith domain plus some constant, which might even change with the domain, times the measure of the domain. So you see here there is some sort of competition because, again, to minimize the eigenvalue, you would like to have the domain as large as possible, but the measure penalization is forcing some balance in this. And okay, and this domain are these joints. And here recall that the first eigenvalue of the Dirichlet Laplacian is nothing but the minimum you get via this Rayleigh quotient among all functions which are 0 on the boundary of the domain. So W1 to 0 is just functions which are 0 on the boundary of the domain. Okay, so this is a minimal partition problem. And now the question is how minimizer of this minimal partition problem look like. And you can run some numerical simulation. So these are actually pictures you get from numerical simulation. And you see that what seems to happen is that these domains, first of all, you don't saturate D, so there are some empty spaces here and there. The domains, they meet just 2 by 2, so there are no multiple points. So if there is a common part of the boundary is just a common part between two domains. So there are no common parts of the boundary between three domains, well, except with the empty sets, with the empty sets with the CM, except with the empty sets, say with a complement of the union. And so this is, and it seems, at least in this numerical simulation, that the domains, they touch tangentially. So actually what you can easily show is that indeed there are no triple or multiple points. So the intersection of any three boundaries is always empty. And the most important thing is that if you fix two indexes, say I and j, and you look to the eigenfunction of di and dj, and then you look to their difference, so ui minus uj, well then, since the eigenvalue is basically given by the minimization of a Dirichlet type energy, you easily realize that these domains, this function is basically solving a two-phase free boundary problem plus some higher order correction, which doesn't really matter for the discussion I'm going to do. Okay? Well, it might, but in this situation, it doesn't really matter. And so you see that if you want to describe what is the behavior of this region, you really have to understand what is the behavior of the positive and negative phase for a solution of this type of two-phase problem. And you actually see again that here is a three-phase problem in the sense that this function v has region where it has to be 0. Okay, so somehow you're really in a situation in which the positive, negative, and 0 phase should live together. Okay, so this is an optimal partition problem, and they come out also in some sort of limiting version of competitions, species competition problems, where somehow you have a certain amount of different species, they want to compete in a fixed region and find their optimal locations, and in the limit of certain parameters going to 0, you get that basically each species is sort of taking its the corresponding region, so it's going to live in the corresponding region. But a very similar problem appeared recently, some years ago, in a paper by David, Filoche, Jerison, and Maiboroda, in which they propose a similar variational problem in order to approximate the location of eigenfunction of operators of the form minus Laplacian plus a potential. This is on a domain D with 0 boundary conditions. So I don't want to enter too much into this model, which was presented by Svetlana, I think, in the last meeting in New York before everybody went into lockdown. But just let me say that basically I mean, up to some renaming, they consider the following problem. So this time instead, so again, you have a partition of a domain. Well, it's not really a partition. You have a certain amount of subset of the domain, di, of a domain D. So you take a number of subset of D and you consider this energy in which, instead of, which is pretty much similar to the one I presented before. So instead of minimizing, so for each domain di, instead of looking to the first eigenvalue of the Laplacian on di, you look to an energy of this form. So basically, here you see, instead of looking to a function which is solving Laplacian v equal lambda v, you look to a function which is solving, so the minimizer of this problem, the Euler-Lagrange equation, will be minus Laplacian u plus vu equal 1, I think. Yes. So, but again, you see that up to some higher order perturbation, you're basically minimizing the Dirichlet energy. So in other words, again, if you take minimizer ui for this problem and then you look to the difference, well, then this difference is a solution of a two-phase problem up to higher order terms, which doesn't really matter in the analysis in this case. So, so again, understanding what would be the location and the shape of these domains DI boils down somehow, at least at the first analysis, to understanding what is the behavior of solution of a two-phase free boundary problem. Okay, so these are the motivation, at least these were the motivation for us to start considering this two-phase free boundary problem. So as I was saying, I'm really interested in the regularity of the free boundary. Okay, not too much of the function, though it's useful to understand the regularity of the function in order to understand the regularity of the free boundary. But I really would like to understand if what appears in the simulations is actually what you can also prove mathematically. And we saw in the picture before that what seems to happen is that, again, there could be all the three phases together, and the positive and the negative phase, when they touch tangentially with, and the zero phase forms sort of a cusp in there, okay? So let me, for this, fix some notation. So I'm going to call gamma the union of, this should be up, the union of gamma plus and gamma minus, where gamma plus is the boundary of the positive phase, so this red line here, and gamma minus is the boundary of the negative phase, so this blue line here, and gamma is the union. So my free boundary is not really the zero set of U, because the zero set of U might have non-empty interior, as we see, but is really the boundary of the zero set somehow, okay? So these are my notations. And let me also briefly recall some known results. So the first thing is that you can prove that the solution is actually Lipschitz continuous, and as we will see, this is the optimal regularity for the solution. So it's basically a function which is differentiable almost everywhere, and the gradient of this function is bounded, but it might be discontinuous, and we will see that it is actually discontinuous, the gradient. And this was done for the one-phase problem, so without any negative phase by Alten-Caffarelli, and by Caffarelli-Friedman for the two-phase problem, and the two proofs are quite different. This one is somehow easier than this one, for some reason that maybe I will be able to comment later on. But okay, this is the optimal regularity. So the second result I want to mention is the regularity for the one-phase problem. So in this case, you just have gamma plus, so there is no negative phase, and gamma plus is actually a smooth surface, basically, with the exception that so okay, in low dimension is actually a smooth surface, while in higher dimension it might there might be a singular set, so some part where the surface, where this boundary actually cannot be represented locally, say as a graph, but this set has a dimension which is quite small, so is at most d minus 5, and so the current best result is knowing that this dimension is at most d minus 5, so there is nothing in dimension 4 up to dimension 4. It might be point singularities in dimension 5. This comes from the work of several people, Caffarelli, Weiss, and this optimal result is due to Jerrison and Savin on this optimal bound on the, well, this bound on the dimension, which is the optimal known bound. On the other hand, this opens the question whether there is a singular set, and there is a singular set. This is due to De Silva and Jerrison, but the first known example of a minimizer with a singular set is in dimension 7. So you see that there is a gap here. So the best, I mean, we don't know whether we can push this example one dimension less, or at least 2 dimension less to match this bound, or we can improve this bound of 2 dimensions to match the example. So there is a gap in here. But this is basically what is known for the one-phase free boundary. So the description is pretty much complete with the exception of this gap on the dimensions, at least for minimizers. Okay, so that's for the one-phase free boundary. So what happens for the two-phase free boundary? Well, here the known result is the following. So assume that the weight you put on the zero phase is larger than the minimum between the weights of the positive and negative phase. Well, in this case, what happens is that the three free boundaries coincide, so that the gamma plus and gamma minus coincide. So in other words, there is not zero phase. So there is no zero phase with positive measure or with non-empty interior. So the zero phase is actually just the boundary between the positive and the negative phase. And this boundary is actually smooth, is fully smooth. So there is no singular set in this setting. And this was basically proved by, okay, it was started by Alt, Caffarelli, and Friedman in 2D. Then it was proved by Caffarelli again in the 80s. And there has been a new proof by the Silva Ferrari Salsa some years ago. And why I'm writing these things in purple, because so this result of Daniela, in which she reproved the result of Alta and Caffarelli, and this via new techniques, and this result of Daniela, Ferrari, and Salsa, in which again they reproved this this Caffarelli theorem. Well, the point is that this proof is what we really used in our proof. So it was pretty much the starting point for our proof, which for the result I'm going to present later. So that's why I'm emphasizing these results. Okay, so these are the known results. And maybe let me comment something about this condition. So what happens when the weight on the negative phase is larger or equal than the minimum between lambda plus and lambda minus? Well, in this case, as I was saying, there is no zero phase. Why that? Well, imagine that you have a competitor, so something which has a positive and negative and a zero phase. Now, you take on the domain, on this domain here, so basically you take the domain which is composed by the negative, so say for the sake of simplicity that the lambda minus, so the weight on the negative phase is less or equal than the weight on the zero phase. Now you take any competitor, you take its negative and zero phase, so basically this domain here, and on this domain you consider a function v which is equal to u on the boundary of this domain, so 0 here, and here equal to u minus, and harmonic inside, okay? So this is my function v here, which has the same boundary value of u minus, so of the negative part of u on this domain, and this harmonic inside. And then I construct a new function which has the same positive part of u, so I don't touch this part here, and I substitute to the negative part and the zero part, I substitute v, okay? So for me, the negative part is positive, so that's why I'm putting minus v here, okay? So this function, so v would be positive because that's the boundary value of a positive. So the boundary value are positive and it's harmonic inside. So it has to be positive, so minus v is negative, okay? So now this w has less energy than u. And the reason is, okay, clearly, I mean, the energy of the positive part is the same, so we don't care. On the negative side, this function is harmonic, so it's going to have less energy than the negative part of u. So on the Dirichlet energy part, you win by easily. And on the measure terms, you win easily again because the measure where w is negative is just the sum of the measure where u is negative and where u is 0. But since lambda 0 is larger than lambda minus, this term here is smaller or equal than this term. Okay, so this is just a trivial computation. So you see that the energy decrease by just, for any competitor, if you just get rid of the zero part, basically you're going to win in energy. So for the minimizer, there is no reason to have a zero part. So the picture would be much more close to this one, in which you have a positive and a negative part, but there is no zero part except for the boundary. So the zero part somehow lower dimension. Okay, so in this case, you are really doing, you are really dealing with a two-phase free boundary problem where you have the positive and negative phase. So, and then Caffarelli in the 80s developed the theory to deal with this type of problems. Okay. So, but let me stress again that the key point here is that there is no zero part. But we saw in the type of problem we were interested in, there is a zero part. So we should be able to deal with it. And if you see the problem I was looking at, basically the weight on the, so let's see for instance here, the weight on the zero part is 0. So it's not smaller or equal than the weight on the positive and negative parts. Okay. So in this case, so what might happen is that when lambda 0, so the weight on the negative part is smaller, strictly smaller than the minimus, then you have a situation in which the three phase coexists, and the point where the three phase coexist are called branch points. So, and you see that the key thing you would like to do now is to understand what is the behavior close to these branch points. Okay, because if you are somehow in a point here in the interior of the, where you don't have any zero phase nearby, locally at least, then here it resembles locally an actual two-phase problem, while if you are here where there is just a positive and a zero phase, your problem resembles a one-phase problem. So the really new point is to understand what happens where all the three phase coexist. Okay, and these are branch points. So let me see what we can prove in this case. So, so if you take a minimizer, and now let me introduce some notation again. So remember, gamma plus and gamma minus are the boundary of the positive and negative phase. Then I'm gonna call gamma 2 phase the intersection of these two sets, and gamma plus minus 1 phase simply the boundary minus the intersection. Okay. So if you see in this picture here, the two phase is the two phase free boundary is sort of this part here where the two phase coexist, which is dotted. I don't know if you can see it. While the gamma plus is just the boundary between positive and 0, and gamma minus is gamma plus 1 phase is the boundary between positive and 0, and gamma minus 1 phase is the boundary between 0 and negative. So the result is the following. So first of all, both gamma plus and gamma minus are somehow C1 manifolds, so are smooth C1 surfaces, possibly outside a closed set to small dimension. That's the same type of closed set of singular set you have in the one-phase problem. And actually what is true is that this is really a one-phase phenomenon. So you see that there are possibly in this minimization problem, there are possible points where you actually, at least locally, looks like a one-phase problem, and it's there that the singular set might appear. So in other words, the singular set does not intersect the two-phase free boundary. So okay, this is somehow is a summarized statement, but you see that it implies also that these two, so that separately the positive free boundary and the negative free boundary are smooth graphs. They cannot cross each other, just that's a topological reason. And so the only possibility is that they touch tangentially. So it's really the picture. So this really somehow justifies the picture we saw before, that the free boundary are, except for this possible singular set, which say we are interested in 3 dimensions, maybe there is no singular set, you really see, or in 2 dimensions, you really see two somehow C1 curves, and which touch tangentially. So let me stress that I'm not saying anything about how bad this intersection can be. Okay, so a priori, for what we know right now, can just be a sort of any closed subset of a C1 graph. Okay, so it's clearly closed because it's the intersection of two closed sets and is contained in a C1 graph. So the intersection of two C1 graphs, but we don't have any structural results on this set at the moment. I mean, we have some hope to get it at some point. But
Guido,
yes.
nevertheless, gamma, the double, the two-phase part, the DP part, that's a closed set.
Yes.
So when you say that the closed set is disjoint from the closed set of singular points, that's the empty set, that's still an assertion that it's definitely away.
Yes, exactly.
It's not touching. That's important. That's a strong conclusion because it's.
Yes. I was to say this. So I mean, it just
You
means that
said it, but I'm just emphasizing.
It's not even in a neighborhood of branch points.
Right.
Yeah. That's. Yeah, I know it's a very synthetic way to write it, but if I should wording this formula, it means that the singular set, it's really a one-phase phenomenon and doesn't get close to the branch points.
The point being simply that they're a fixed distance apart.
Yes. Yeah. So in a sense, we can almost say that there is no I mean, for the peculiarity of the problem, which is really studying the branch points, there is no singular set in there. Okay. So this is the result, and let me also mention that this result was proved in 2D by Luca and Bosch there via completely different techniques with respect to ours. So this is based on what is called an epiperimetric inequality, for those who know what it is. And this proof does not apply at all in higher dimensions, so that we have to change pretty much the strategy of the proof. We try to adapt this technique to higher dimension, but we failed miserably. So, okay, so this is the main result. And maybe in the last 5 minutes, I might try to give a very rough idea of how the proof works. Okay, so this proofs works. So that's going to be a bit more technical, but the proof works following a strategy which is now customary in this type of problem and has its roots in the regularity theory for minimal surfaces done in the 50s by a series of authors. Just too long to recall here. And it's based on blow-up analysis. And so there are two main steps. One is the blow-up analysis, so sort of an infinitesimal analysis. And the second one is an epsilon regularity theorem, which is a sort of stability analysis somehow. So blow-up analysis will give a sort of infinitesimal regularity, and the epsilon regularity theorem is what upgrades this infinitesimal regularity to some sort of size 1 regularity. It's very tough thing. But before going through the main steps of the proof, let me, so it's important, so once you have a minimization problem, what is important is to understand what are the optimality conditions of this minimization problem, because it's basically the only thing you have at your disposal to try to prove something. So what are the optimality conditions? Well, the first easy optimality condition is that the function is harmonic where it is non-zero. Okay, that's what I was saying. Where it is non-zero, you can perturb the function keeping it non-zero, and now you want to make happy only the term with the Dirichlet energy. Okay, so you have to be harmonic. So the key point here is what are the conditions on the free boundary, and to understand what are the conditions on the free boundary, what you would like to do is really to move the free boundary, because as soon as you don't move the free boundary, there is nothing which you can deduce. And how do you move the free boundary? You move the free boundary via vector field X. So basically what you do is that you take a vector field X in your domain, use this vector field X to generate somehow a family of diffeomorphisms. And now you precompose U with this family of diffeomorphisms. So you see, this is a family of diffeomorphisms. This here, X plus epsilon capital X, which like moves the domains into itself. And when epsilon is equal to 0, it coincides with the identity. So this means that for epsilon equals 0, this functional has to have critical points. So you know that the derivative with respect to epsilon, when epsilon is equal to 0, has to be 0. So instead of doing this, let me do, at least in the 1D situation, let me do a more by hand analysis, which I think is, and which will give us even more precise optimality condition. So again, in 1D, what we know is that the function is harmonic, but it's non-zero. So basically it has to be just a linear functional when it's non-zero. And now what we don't know is what these slopes are, right? But what can we do to at least get some relation between these slopes is to sort of move these points. So move the 0 around. So we can do in two ways. The first one is just we keep, say, the negative part equal, and we just move a tiny bit on the right, the positive part. Note that we can just move it on the right? We want still these things to be a function, so we cannot move it on the left, meaning that epsilon has to be positive in this type of deformation. So you get this possible competitor here, if I didn't mistake in the formula. And now once you compute the difference in energy, you see that at the first order, this is alpha square, where alpha is the slope of the positive part. So that the term which is linear in epsilon is alpha square minus the difference in weights between the positive and the 0 part. And these things has to be positive no matter for every epsilon positive. So you don't actually get an equality, but you get an inequality, which is this one. So alpha square, so the slope of the positive part, which is nothing but the gradient of the positive part square, has to be larger or equal than lambda plus minus lambda 0. Okay, so this is a type of deformation you can do. And the other type of deformation you can do is just to move all together the positive and the negative part. So this time you can move this on the right or on the left, right? Since you're moving them together. So your competitor now has this formula here. Now you expand the energy to the first order in epsilon, and you see that this time this quantity has to be positive no matter what is the sign of epsilon. So it means that it gives you an equality in which alpha square minus beta square, which is just the gradient of the positive part minus the gradient of the negative part, has to be equal to lambda plus minus lambda minus, right? And somehow you can do a similar analysis when you just have the positive and the 0 part or the negative and the 0 part. So you see that there are transmission conditions. And so you have a coupling between transmission conditions. So you know that what is somehow the jump of the gradients, and some equality and some inequality, sorry. So you know that the gradients of the positive and the negative part cannot be too small by themselves. So in other words, these are the optimality conditions you get. So you are harmonic where you're non-zero. You have this transmission condition on the positive free boundary, on the one phase free boundary. You have this other transmission condition on the two phase free boundary, and globally you have this inequality in the gradients. Okay, so these are somehow, at least formally, the optimality condition you expect to find. So maybe. Okay, I think I think I'm running over.
I think you're okay here. You have you have 10 more minutes, believe it or not. So
okay,
you're safe, but you know you don't have to go the whole time. It's relaxed. Take it easy though.
Okay.
Sorry,
okay.
No, I'm wrong. Maybe you only have 5 more minutes. That's right. But there are a few minutes at the beginning, so you have 5 plus a little fudge room.
So again, as I was saying, so the first step in the analysis is this blow-up analysis. So how does this blow-up analysis works? So now what you do is that, say that you have your minimizer with this positive, negative, and 0 phase. Now you take a point on the free boundary, call it x0, and you would like somehow to zoom the behavior of your functional and of your problem around this point x0. So you would like to take a small ball around x0 and make it a large ball, say, of size 1 in order to see what is happening there. And the natural way to do this is to perform this type of scaling here. So you take a function, your minimizer u, and you make it somehow, and you scale in this way. So you zoom in this way to make it of order 1. So remember that the function was Lipschitz. So basically, and in x0, it was 0. So basically, in a ball of radius r around x0, the size of the function should be of order r at most. So if you divide by r, you get something which is of order 1. So this is really somehow describing the infinitesimal behavior there, okay? So, and what you can prove is that this is actually a compact family. So there is a limit when you send r to 0. Well, maybe possible different limiting, depending on the subsequence. But for any sequence of r going to 0, you can extract a further subsequence such that this thing has a limit. And this limit is what you would expect to tell you what is the infinitesimal behavior of the free boundary there. And what actually you can prove is also that these limits are one homogeneous. So you expect that when you zoom around the point, there should be some simplification somehow, right? You should somehow kill some complexity of the problem. So if everything were smooth, you would expect to see somehow just the Taylor expansion here. We don't yet know that something is smooth, but at least what we know is that there is a one homogeneous minimizer. Okay, so you gain some symmetry somehow, at least dilation symmetry. And this is actually non-trivial and is due to the bias monotonicity formula. Now, imagine that my zoom was done in a regular point. Okay, so a point where I know the free boundary is actually a smooth graph. Well, then what I see depends on where I'm taking this zoom, but basically, if say I'm taking the zoom on a point which is between the 0 and the negative phase, what I'm going to see is a function which should depend just on one variable, the variable's normal to the smooth free boundary here, and whose profile is really the one of a one-dimensional solution. Okay, so you see that is a sort of Brooklyn linear function. And now you see also that the Lipschitz continuity I was mentioning at the beginning is optimal, because this function has a discontinuity in the gradient. So that's what is happening on one phase point. On the two phase points, you might see that two linear functional with different slopes. Okay, in this picture, they don't really look different slopes. And the other thing, you know, as I was saying, is that so you have this transmission condition on two phase points, and you always have this inequality. It's a global inequality. Okay, so this is what you expect to see in a smooth point, and now you do the other way around. Now you call a point regular if there is at least one of these possible blow-ups which is somehow one-dimensional in this sense. Okay. So in other words, if along one sequence of radii is going to 0, your free boundary would become in the limit and a hyperplane. So you call this point regular. And now what you want to prove. So the first thing you prove is that actually with this definition, regular points, so singular points, so the complement of regular point is quite small. This comes from a classical tool in geometric measure theory, which is called feather dimension reduction. And these are the sets sigma plus and sigma minus we were mentioning before. But now you see that the definition of regular point is pretty much horrible, because I'm saying that there is one blow up which is flat, but I have no idea, neither than there are no other blow-ups which are not flat. So in other words, that depending on the scale I'm looking the free boundary, I might see very different behavior, or maybe all blow-ups are flat, but they are not the same. So this is a sort of spiraling behavior of the free boundary. So so what you need to do now is sort of to upgrade this infinitesimal definition to a sort of size 1 regularity. So the difficult part is showing that if you have a regular point, then really the free boundary is smooth in the neighborhood. And this is what the epsilon regularity theory should tell you, and that's where the work has to be done. And again, so this epsilon regularity theory somehow was known at one phase free boundary or in points which are at the interior of the two phase free boundary, where you actually see really two phases. So the new thing to add here is to understand what happens at branch points, and then okay, it's to understand what happens at branch points and somehow to have everything talking together. So you want to know that if you want some smooth, globally smooth thing, you need also to patch the estimates you have between different points. Okay, so I won't give you the details of the proof, but maybe I can give you an idea of what is happening when you look at one phase points. And this is somehow the proof of Daniela for one phase points. So now assume that your blow up, you can, so you're in one phase problem, and you can somehow renormalize the parameter. So you might expect that your blow up, so the real infinitesimal behavior is something like the positive part of x1. Okay, so you have that your function should somehow, when r is quite small, should look like x1 plus. Now you write it as x1 plus a tiny perturbation, epsilon times v epsilon, where v epsilon is chosen in such a way that, so where epsilon is chosen in such a way that v epsilon is of order 1 somehow. Okay, you can always do this. So what are the equation which v epsilon is satisfying? Well, basically you have to linearize your problem. How you do that? Well, the first thing is that it's easy to see that v epsilon is harmonic where u is positive. But now since u is almost x1 plus, the part where u is positive should be almost b1 plus, right? And okay, so this is somehow the trivial thing. And then the interesting thing is what happens if I sort of linearize the free boundary condition. So we know that the gradient of the positive part square should be equal to 1, which in this case is lambda plus minus lambda 0. And now if I expand these things, what I see is that basically this means that remember that this is b1 plus and u positive should more or less be b1 plus. And now you see that the one derivative of v epsilon should be 0 on the boundary of u positive, which should be more or less equal to x1 equals 0. So in other words, v epsilon is basically almost a solution of a Neumann problem on the half ball. But now the regularity theory for the Neumann problem on the half ball is well known. And the key point is to somehow pull back this regularity theory from the Neumann problem on the half ball to our original problem. And this is done via an iterative techniques in which you somehow try to correct at each step your blow up by using the gradient of the Neumann solution, and you iterate these along scales. Okay, so now the things become a bit more technical, so I don't want to enter in this, but that's the key step here. So the first thing, so there are two things, one which is clear by this proof, which is you need to understand what is the linearized problem, and the second one is actually that you have to, and it's technical, but it's the key point, you have to have enough compactness to move back and forth this type of estimates. Okay. And now, okay, just maybe one slide. What happens when you actually have a two-phase problem? So here, these times you would expect that, so say that I'm normalizing constants such a way that my blow up will be like x1. So I would expect u to be some perturbation of x1, where with two different perturbations on v plus epsilon and v minus epsilon on the positive and negative part. And again, I would like to understand what are the conditions for this v, what are the optimality conditions for this v plus and v minus. And what turns out is that this v plus v minus, they are somehow solving a I would call it a thin two membrane problem. So basically this has to be harmonic on the positive and negative half balls. And then, so the V plus and the V minus are harmonic on the right and on the left. They satisfy a Neumann condition where the trace on the hyperplane is not the same, and they satisfy the transmission condition on the part where the traces coincide, and they always satisfy an inequality. So their normal derivative is always positive. So that the x1 derivative is always positive. So you see that this corresponds, this condition corresponds to linearizing this type of condition. This condition corresponds to linearize this type of condition. And this condition here, the inequality, corresponds to linearize this condition. So now, if you get rid of this last inequality, there is no really good regularity theory for this type of problem. So the key point is that once you add this condition here, then this problem has a good regularity theory, and actually solutions are slightly better than C1. And now, once again, you can sort of pull back this regularity theory and move it to the two-phase problem. Okay. So maybe in this 30 seconds, so said in this way, it looks quite easy, but the key point here really is how to get the compactness of this perturbation in such a way that is meaningful to move regularity theory from one side to the other. That's where the actual technical point is. And the point is that these solutions are bounded in L infinity. So these perturbations are bounded in L infinity by the way we choose them. But now you would like to have at least L infinity convergence, and this is not enough if you're just bounded in L infinity. So basically, you need to get some sort of compactness in the topology where you are bounded, which is non-trivial. And this is still somehow a nonlinear phenomena because you are doing it before going to the linear problem. Okay, so that's where this very nice idea of Daniela is to adapt this partial Harnack inequality of Savin to this type of problem, so you can sort of get enough compactness to pass to the limit. And if you want the second problem, but this is less challenging, is that your functions are defined on domains which are changing with epsilon. So in the limiting procedure, and you have to take care of these domains because you really are interested in what happens up to the boundary of these domains, because this is like the boundary, the free boundary, okay? And the convergence is quite weak. So you have to deal with these things. And the third problem is that, yes?
I think maybe we need to wrap up.
Oh, yes, this is my last slide.
Okay, good.
So the third problem, which again looks a bit technical, but was another key step, is that, I mean, when you do an epsilon regularity theory, it might happens that your ball is not really well centered in the point you would like to analyze. Since it's a size one theorem, is not really that you can get any information on the you cannot propagate any information on the center of the ball. Now, if your ball is a bit off-centered, it might be that your solution is better approximated not by an actual blow up, but by a solution which is somehow broken in this way. So this is somehow the best approximation you can do of your solution. So this cannot arise, this type of picture cannot arise as a blow up, but it can arise as in the study of the compactness. So, and you also have to deal with this type of situation and to understand how to get compactness in this situation. That's somehow the key point of our result. And with this, I conclude. Thank you very much.
Thank you, thank you. Other people are applauding, perhaps virtually. So I think we have a few minutes for questions. I'll open it up. Anybody can just interrupt if they want to put questions in the chat. I'll try to read them. But why don't we go ahead, and I'll open it up for questions now.
So I thought you wanted to ask a question, but since you're not fast. You said that you were talking about constant coefficients. So sorry, this is Guy David.
Yes.
Was it for the convenience of a lecture, or I mean, if the coefficients vary in a Hölder way or something like this? That's still true.
So it should work again with Hölder coefficients. So we didn't prove it actually. So the paper is with constant coefficients because of the application we had in mind. I think the strategy works also with Hölder coefficients. It should work somehow.
And you don't have conditions on the fact that some lambda would be larger than the other one or something?
Sorry?
Which is, I had a nightmare, which is these conditions that lambda plus would be larger than lambda minus, or some business like this.
No, so the point is that they should be separated from zero. So we don't know what to do if one of the two is zero. But as soon as the lambda plus and lambda minus, they are separated from zero, I would say that we should be able to deal with also with some perturbation. This technique should work also with some perturbation in there, I think. So that's what you are doing somehow, right? That's the line of research here.
And I have another question. Suppose even in dimension 2, do you know that a triple point is isolated or not at all?
No, this would be great. So I would suspect, but we don't know it.
So maybe this is a moment to enter into a similar sort of question. When you're sort of getting closer to one of these isolated points, let's just pretend that we already know it's isolated. Do you have some idea of what I mean, you proved a compactness theorem, so you have to have at least some idea what the cusp looks like, what the spread looks like. Maybe this is obvious in 2D.
So actually for the compactness theorem, you don't really need it because, so the point is this one, what you get in the limit is basically a thin obstacle problem. So the optimal regularity for the thin obstacle problem is C1 1/2. But for getting compactness, somehow you need to have a robust proof of Hölder continuity for the thin obstacle problem. So Hölder continuity, so just before C1. So Hölder continuity for the thin obstacle problem, it's not hard to get it. So
I see. So this is because you're down near C0, so you're not in trouble with this delicate issue of the shape.
So the expansion somehow in the cusp is a very interesting thing, which we are trying to get. But there you need to, so you should be able to know this for the actual thin obstacle problem, so for the linearized problem. But here now you want somehow to move this expansion back to your original problem, you need to get a higher order compactness in a sense. So that's this C alpha compactness was enough to get a C1 alpha regularity, which might look strange, but that's actually how this type of proof works. But now if you want to get higher regularity, or well, actually higher regularity shouldn't be possible. C1 1/2 should be the optimal one, but nevertheless you might try to make an expansion. So in a sense, you know what should be the model problem in the limit. So you might try to make a sort of Taylor expansion in terms of this type of problems and to describe the cusps to higher and higher order. But that's, yeah. But in a sense, the first question here we don't know how to answer is to say that this branch points are, for instance, in 2D isolated. So we know this for the limiting problem. So this is known for the thin obstacle problem, but already we don't have enough compactness somehow to know this for the limiting problem. Because in a sense, it's a sort of a unique continuation business, this one. So the point is that if they are not isolated, so what happens is
and there's a cluster point, right?
There are cluster points, and then it's easy to see that somehow the order of contact with this. So imagine like just one of the two free boundary to be flat, the order of contact should be very high. It should be, and so this, for the regularity theory, you are very happy if you have an infinity in order of contact, right? So the decay is super good, but for this type of analysis, you would like to rule out this infinite order of contact. So this is much more related to unique continuation somehow.
Yeah.
So there is some hope. Well, at least I don't know if there is some hope. We are trying to
Very good.
that,
So thank you very much. Thank you, Guido, for a beautiful talk. We're going to take our break now because we have a next talk coming up at